Welcome to Frank Stajano Explains. Today's topic is exam question walkthrough. We are in exam season, and so I'm going to take you through an algorithms question. But before we do that, as I told you other times, you should not look at the solution before having attempted the question yourself. In fact, one of the most popular videos on this channel is one in which I give you 3 secrets for getting good marks in the exam. And one of these 3 secrets is precisely a foolproof recipe for how to tackle exam questions in preparation for the real exam. So go and watch that video again and follow that recipe to the letter. This involves doing the exam question yourself in exam conditions and then a variety of other things before you even peek at the solution or at this video which contains the solution. So here's the exam question. Stop the video, do it on your own, and when you have got your best attempt, which you have done in no more than 30 minutes, then allow yourself to watch the rest of the video. See you. Stop the video, come on. Go and do the exam question yourself. Okay, so this is a question that I set about 10 years ago, which starts with a mathematical hint. Okay, mathematical hint: the following series converges to the indicative value if the absolute value of x is less than 1. All right, great. Maybe I did that when I was little. I certainly forgot, but it may come in useful. Well, hopefully it will come in useful somewhere through these answers. We'll find out. Part A: you're given an unsorted array of n items, of which you must return the top k in any order. Already smells familiar. Give a clear and accurate description of 2 efficient algorithms for solving the problem, following the hints below, and derive their time complexity in terms of n and k. First hint is, for this attempt, use a priority queue. And this is what I was already thinking about when it said, you must return the top k. Actually, it says in any order. I can return you the top k in order from smallest onwards by using a priority queue, a heap, a min heap. So when the question asks me give a clear and accurate description of 2 efficient algorithms, efficient must be in the context of some kind of baseline thing. I mean, if you do this, then nobody's going to be impressed. It's correct, but that's fine. And that would be the baseline of saying, well, if you're given an unsorted array of n items, you could always sort the array at cost and big O of n log n, and then take the top k items. And so taking the top k items, either you just directly give a reference to the array in place and it has constant cost, or even if you have to output them one by one, it would have cost big O of k, which, since k is less than n, is included in n log n. So anyway, the overall cost is n log n, and that's it. Everybody go home. At cost n log n, I can solve this problem. So anything you do, if the total cost is n log n, it won't count as efficient because there's already an obvious way of doing it without having to spend any time on it. So if I use a priority queue, do I manage to do this in less than n log n? Well, first I have to build the min heap, but we have done an entire video on the fact that it is possible to build a min heap out of an unsorted array simply in linear time. So this part only costs big O of n, still less than n log n, so I have a chance of getting things right. And then how much does it cost me to return the top k? Well, every time I just do extract the minimum at cost log n, and I have to repeat that k times, so k times log n, plus the n that I paid earlier. So the baseline cost is big O of n log n. And my solution for the first step with the min heap is big O of n plus k times log n. Okay, and I am being slightly sloppy here because I use big O notation with 2 variables, and we never really explained how this should be done, and this actually is more complicated than one might think. But okay, the question asked me to do this stuff, and I'm going to do this stuff, and I'm pretending that everybody's okay with that. Let's just not dig deeper into that. I am answering the question. I'm not trying to give another lecture. And this arguably, for a small k and a large n, is going to be smaller than n log n. And That's my solution for number 1. That was easy, and so it only earns me 2 marks. Now I should be slightly worried that I have something which requests 8 marks. So that's usually the hint that I have to think harder. For this attempt, start by finding the kth largest item as when computing order statistics, and describe all the steps in detail. Right, okay, so well, I see where this is going. I remember the quicksort business where I had a partition procedure that would split the unsorted array into things that were smaller than the pivot and bigger than the pivot, and the pivot in the middle. Actually, to be precise, one of the 2 sections had or equal as well. And I could use that to find the kth largest item by recursing only in one of the 2 sections instead of recursing in both. And then there was the maths I could develop to prove that in that case, if the split was broadly even, then the recursion solved to big O of n as opposed to big O of n log n, as in the case where I have to recurse on both sides. So I apply this strategy to this case, and what I do, I have to describe all the steps in detail. Well, I have my array. I use the partitioning procedure from quicksort, so I pick some pivot in some way, and maybe just the last element, or maybe I pick it at random, whatever. And then I end up with 2 regions. Things that are less than the pivot, then in the middle I stick the pivot, and then things that are greater than or equal to the pivot. All right. So then I find where is the position k. If position k is somewhere here, in this region, then all these things are going to be part of the top k elements. This one also is going to be part of the top k elements, and these other ones are going to be part of the top k elements. So I just repeat the work on this section. And I recurse into that. If instead the k was exactly the pivot, then all right, all these things are part of the top k, and this is another part of the top k. That's great. And I stop there. I don't have to recurse anymore. And if instead the kth position was somewhere in this region, then because the elements in this region are still unsorted, I can't really tell anything about what's to the left or to the right, and I have to recurse into this particular section with a smaller set of things to a smaller set of unsorted elements to look from. In the case where I recurse in this other region, there's the thing I should note is that if this was k, the original thing, here is going to be k minus the original k minus this section, which I no longer have to count because I've already considered them as part of the top element. So k minus something over here is going to be the new value that I stick in, and the new array is going to be just this. Anyway, so this all sounds pretty straightforward, and I'm not too sure why I would get 8 marks for doing that. This seems pretty generous and pretty similar to what was already in the lecture. So I basically get 10 marks almost for replicating bookwork, except applying it to a slight variant to what I had done earlier. So I'm happy I started the day well with 10 marks in the bag. Now the next part, and I haven't yet used any of my mathematical hint, so maybe this shows there may be trouble later. Who knows? You are given a hash table that stores n keys. All right, it has m slots. All right, that's seems like a regular hash table. Hash table, m slots. Collisions are solved by chaining. Each hash table slot contains a pointer to the head of the corresponding chain, so I have little chains that go out from here like that. Each one of these has its own pointer to a little chain. Okay. No elements are stored in the table itself. All right. the table itself just contains the pointers to this, and no chain is longer than L elements. So the longest of these chains is at most L elements. Each slot has an extra field giving the length of the corresponding chain. Okay, right. So I'm going to do this, and there's going to be something that says L0 here is maybe 35, and L1 is the length of this other chain, L2, and blah, 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 blah. An extra field giving the length of the corresponding chain, which of course I have to update if I insert or remove elements in that chain, but that's not my problem. Now, give a clear and accurate description of an efficient algorithm for returning a random key from the table, such that each key has equal probability of being selected, and analyze its time complexity. Assume the availability of a function random x that returns in constant time a random integer between 0 and x. Okay, so first thing that comes to mind, I select one of the chains at random, and then I select an item from that chain at random. And just thinking about it for more than a few seconds shows that this is a bad idea, because the chains are not all the same length. So once I have selected one of the chains uniformly at random, the fact that some chains are longer and some chains are shorter makes it so that depending on whether I hit a long or a short chain, the probability of each individual key in that chain is going to vary. If that that chain here had length 100 and that chain here had length 2, then each element of this chain would be 50 times more likely to be selected than each element of this chain after having done an equal probability selection between this chain and this chain. So that doesn't work. So what would work? Well, I say, okay, let's go back to first principles. I have a total of n items in here. So if I just select a random number between 0 and n minus 1, I could point at one of them and then I'd have to go and pick it up. I mean, I could linearize all this by just threading all the chains one after the other and then selecting the ith item of that mega chain, assuming I is equal to random between 0 and n minus 1. So it seems fairly inefficient to actually build the composite chain. I could just go in the place where I should go by looking up things from these lengths. So if my I equals random n minus 1, then what I do is simply compare this I with the various L0s, and if this L0 is less than I do I minus L0 and I move on to L1, and if this is still less, then I keep subtracting until I get to the place where it says, well, this slot must have your item, and at that point I have to walk through that chain. So I don't walk through all the chains as I would if I had concatenated them. I instead skip all the ones where I'm sure it's not there, and then I only walk through the last one. And so the maximum cost of this walkthrough is going to be L, because I was told that this was the maximum length of a chain. So this thing here is L at most. This thing here was M. So I may have to pay up to M of these subtractions to decide which chain to go into. And when I find the chain to go into, then I may have to pay up to L to walk to the right key, because in the worst case it might be the last one over here, and in the worst of the worst cases it might be the last one of the longest possible chain, which was L. So this second thing will cost me big O of M plus L. Again, I'm sweeping under the carpet the two variables, but never mind that. I mean, even the question is doing that, so surely I'm allowed to do that. But this note says the time complexity of a reasonable algorithm will not exceed big O of M plus L. It kind of is comforting to know that what I did is considered a reasonable algorithm. I mean, it certainly is correct, as opposed to the first one, which is incorrect. It's correct and has reasonable complexity, but solutions awarded full marks will improve on that. And I would rather have full marks, so let's see if I can improve on that. Well, is there anything I can improve over here? If I have to solve an algorithmic question, I've already got some kind of upper bound. I can do this. Is there a way that I can do better than this? Well, the things that I'm doing here, the m is the cost of going this way, the l is the cost of going this way. If I leave the things where they are, once I identify with the random selection the key that I want to pick, then for actually getting to the key so I can read it out, I need to walk the corresponding list. And that list could be the longest list, and that key could be at the end of the longest list. And in that case, I'll have to pay L to get there. That is a cost I don't see any way of reducing. The only where I can see I could make some savings is not paying a linear cost in the number of slots for selecting which list to pick. How could I do that in less than linear cost? Well, I could adopt a rather different strategy, which consists of considering this as a rectangle full of keys. Well, not really full of keys, a rectangle partly filled with keys, but with some kind of boundary here, like this, kind of a skyscraper skyline on the side, where this list is only up to here, this list is up to here, this list is up to here, and so on. Maybe one list is all the way to L, but there's going to be some region here without keys, and some region here with keys, with an irregular boundary. Okay, so if I select an item from this rectangle at random, uniformly at random, I can do that in constant time just by saying, okay, pick a number between 0 and the maximum number of things that are in there, which is m times L, m times L minus 1 to be pedantic, random of this. This gives me the index of one of these positions if I linearize this array. So I just divide this by m to get which row, and then do modulo m to find which column. And the snag is that by doing this in constant time, I identify one cell in this rectangular array, but it could be in the green part or it could be in the red part. And if it is in the red part, it means I didn't hit on a key. On the other hand, if it does end up in the green part, I hit on a key at random because I picked one of the possible keys at random. I could have picked something that was not a key, but certainly if I hit on a key, it was every one of the keys had equal probability of being picked. If I hit on something that is not a key, I basically wasted my chance, but I can always give it another go. I can repeat the random procedure, which after all had only constant cost, and I might get lucky this time. If I get lucky, then there we are. I've just wasted one attempt, and then I deliver this. Still less than m, actually. And that's my intuition as on how I can improve on this. I can do big-O of number of times I do my selection procedure plus L for walking to actually going and fetching that key once I found that it's going to be in there. Whether it's there or not, I tell by looking at the coordinates and seeing if the column coordinate is within the length of that slot. If it's not, I already know that I failed without having to walk through that list. So I know in constant time after selecting an item whether it is in the red or the green part. If it is in the green part, then I have to pay up to L to actually go and reach it. But I do that only on success, so I'm not that worried about it. So the question is the number of rounds of throwing the dice to find my random key going to be less than m? If I manage to do something that's less than m, then I will have improved on this reasonable algorithm, and I will hopefully get the full marks. So how would I go about ascertaining whether the number of throws of the dice is less than m? Let's try to count them in the first place and see what comes. I have a hunch that it will be less than m, but I have to be slightly more rigorous, and perhaps this is where this mathematical hint will come through. So let's make ourselves a little more space by scrolling all this stuff down and see, skip the hint here just in case. See if we get anywhere. So what is the probability that when I throw the dice, I actually get success? I get something that was in the green region. Well, the probability of success is equal to the number of keys that exist over the number of cells that exist. Like that. And the probability of failure is the complement of that. So how many times do I have to try? Well, I have to try until I get success. And I get success in one of the following ways. Either I just get success with probability P. So I start and I throw the dice. Either I succeed, probability P, or I fail, probability Q. If I fail, I keep trying, and in this case, either I succeed with probability P or I fail with probability Q. And if I fail, I try again, succeed with probability P and fail with probability Q, and so on and so forth. So this one, this leaf here has overall probability P. This leaf here has probability QP. This leaf here has probability QQP. This one has QQQP. And you see where this is taking us. So the case where I have made m attempts will have had m-1 failed attempts and 1 successful attempt. So in total, the number of attempts I make is the weighted average of the lengths of these tries weighed by the probabilities. So this is only one try, probability P, 2 tries, probability QP, 3 tries, probability QQP, 4 tries, QQQQP. And if I do m tries, this will be weighed with probability QQQQQ n-1 times P, Q n-1 P. And if I sum all these from 1 to infinity, then I get the expected number of attempts that I have to make. So the thing that would end up in the formula big O of something plus L, which I hope is going to be less than M, the dot dot dot. So this thing here is suspiciously similar to my hint. In fact, it's super similar, except X is called Q and M over here is m-1. That I can cure very easily by just multiplying by Q, and I divide by Q in front, and this P, I can take out the summation since it's not a function of M. So I have a P here, then a Q here, so that I can afford to multiply by another Q, and this becomes MQM, M equal 1 to infinity. And now this part here is exactly the same as this, except I'm calling the X, I'm calling it Q. So I can then substitute my hint into here, and the summation becomes X, which is Q, 1 minus X, which is 1 minus Q squared, and so these Q go away, and 1 minus Q, since P and P plus Q made 1, 1 minus Q is actually P, so this is P divided by P squared, which is, of course, 1 over P. 1 over P. Wow, that simplified a lot more than I imagined at first it would. So this is a good sign. It was probably planned that way in some sense, otherwise they wouldn't have set it as an exam question, because they're not that evil. And all right, so if it's 1 over P, 1 over P, that's going to be equal to what? Since P was this, it's going to be equal to MLN. And is this number less than M? Well, it is less than M if this fraction is less than 1. What was L and what was N again? So I had this rectangle here, the ragged border, and this was the part with the keys, of which there were N, and this was the part without the keys. and L was this, was the width of this rectangle. So it should be obvious that if one of these things, if L is the maximum length of one of these lists, then at least one of these is L, and so plus there's more for all the others, and so N is substantially bigger than L, and if N is bigger than L, then this number is less than 1, and so this total thing is less than M, and if I stick it in here, M, L, N over here, then this thing is an improvement over my baseline, which I'm going to bring up again. Time complexity of a reasonable algorithm will not exceed big O of N plus L, but solution of the full marks will improve on that, and I have now improved on that, so I am hoping to get my full marks. Now, someone who were extremely pedantic in a mathematical sense, which is not uncommon among computer scientists, would notice that no chain is longer than L elements is not the same as saying L is the maximum length found amongst all the existing chains. It could be that the chains are all, 997, 995, 982, 999, and you can say no chain is longer than 1 million, which is true, but not particularly useful. It's the kind of thing that an annoying mathematician would tell you. No chain is longer than 1 million. Well, that's true, but I'd like it better if you told me no chain is longer than 999, because that is a tighter thing. So if with the problem as written, strictly speaking, if L is just a bound that is not guaranteed ever to be met by any of the chains, then I cannot say that this fraction is necessarily less than 1, because L could be 1 million gazillion and would exceed the N, even though the N is two-dimensional, if you pardon my loose speaking. But let's not worry about that. Certainly, if I were marking this question and you had produced all this stuff, then I would have awarded you the full marks in recognition for that. Now, if you say, well, okay, I'm thinking of something I could never derive this thing with a probability. Probability I did when I was in kindergarten, and now I have completely forgotten all of that stuff because it's not something that I do. Well, first of all, very basic probabilities like this is a good idea to be still moderately fluent with. After all, I only had to do 1 line's worth of it, not 2 or 3 blackboards worth, and so plus I had a hint that did most of the heavy lifting. So first of all, don't be scared by having to do a bit of equation, and secondly, I would have given most of the marks for thinking of the strategy of, instead of hitting precisely on a key that I select with uniform probability, I give myself the freedom of hitting somewhere where there might not be a key, and if I fail, I try again. So that is the crucial insight from an algorithm's viewpoint, and I would have given you most of the mark for doing that, and then an additional cherry on top for actually working out the maths and using the hint and all that stuff. But coming up with the lateral thinking strategy of trying and allowing yourself to fail and trying again, and thinking that you might pay less by failing a few times and trying again than by doing the thing precisely, that would have been most of the reward in an algorithm's context. So if you had not been able to do that, but you had clearly explained, clearly is crucial here, clearly explained the other strategy and the reasoning why it would be worth attempting in your opinion, then you might have got most of these marks, in the order of 17, 18 instead of 20. Anyway, I hope this gives you ideas on approaches for tackling unusual questions. Hope it also gives you some feeling for the fact that not all the marks necessarily weigh the same. If I look at this, then I have half the marks for this initial part, which is largely bookwork, and half the mark for this one, which requires quite a bit more creativity and insight If you had just got to the reasonable algorithm like this, you would have got maybe a little less than half the marks, I guess. And that insight was the extra bit. But the amount of effort you have to put in tends to be proportional to the marks awarded, except it's not quite a linear thing, because we do want people to pass the exam. And so we give you easier parts that are easier to chew on, and almost everyone should be able to get a few marks. And so you can select the parts you can do, and at least do those. It's better than leaving it blank. And so it's easy to get these first 10 marks. It's hard to get the next 10 marks. But within those 10 marks, it's certainly easy to get the first half of these marks for just doing the basic thing that does not exceed big O of n plus L. And plus, the extra final bit, well, that will require more effort, but that's how you how much you have to invest if you want to have the top mark. That's more or less how things are structured. Maybe I'll do another video on how an examiner sets an exam question and what kind of things we're trying to extract from students by the way in which we ask the exam question. Anyway, but that's a story for another time. If you enjoyed this, please stick a like on this. If you want more like this, then let me know in the comments, and also follow the channel for other things along these lines. Thank you very much.